Alright guys, I'm going to try to make this video without any interruption. So today we're going to go over strings and dynamic programming. Now before you keep watching this, please hit the like and hit the subscribe button below, because I like to know that some people are watching. Some people are actually watching these videos that I make. So we're going to talk about strings and dynamic programming. What are strings? Well, we use strings the whole time in C++. They're basically, well, in C it's an array of characters. But in C++, string is basically a separate class that allows you to manipulate characters, right? So we're going to talk about strings, and we're going to talk about dynamic programming. Dynamic programming is actually a very important tool in algorithms and data structures. Now, dynamic programming is basically a way of breaking down a complex problem into certain subproblems, and then you're basically storing things in an array, your previous solution in an array, and then in order to look it up quickly. It's basically the gist of it, but we're going to go over that. So first, we're going to talk about string operations, the STL class. Then we're going to talk about dynamic programming. We're going to talk about pattern matching, compressions, greedy method, and then tries. Tries, which are just like standard tries, compressed tries, suffix tries, and then search engine. So what are strings? So document processing is rapid dominant function in computers. So making sense of these terabyte information requires an amount of text processing. Text processing algorithms help you highlight some algorithmic design patterns. The design pattern matching gives rise to something called brute force, which is basically inefficient but has a wide applicability. For text compression, we could apply a greedy method, which allows us to approximate solutions to hard problems, and for some problems, they give rise to optimal algorithm. Finally, in discussing text similarity, we introduce dynamic programming, which applies to special instances to solve a problem in polynomial time, and that appears to, at first, to require exponential time to solve. So here we have text processing. So at the heart of algorithms for text processing are methods for dealing with character strings. Following are the examples of strings. Strings are basically an array of characters, right? And at least in C++, it's kind of the same thing, but now you could have methods, all right? So P is this huge string of characters, CG to whatever, and S is also another string. This is just a URL link to some website. So they're just saying that to get a substring of it, it's like a piece of this string, okay? Like if you want to get a certain piece of the string, you use a substring. That's what this is saying. So like if I want a substring, so strings, like I told you, are an array of characters, right? So they start at index 0, 1, 2, 3, 4, 5, 6, 7. Like start at 0 and end at the size -1. So here I have 0, 1. Okay, so here, okay, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So there's the index ends at 22. But there's 23 characters in the string, because if you count it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Yeah, so there's 23 characters, and there's the index ends at 22, because you start at 0. So if I want to get a certain substring of this string, easy. Basically, you're going up to, but not including the last index. So if I want a substring from 0 to 4, so 0, 1, 2, 3, 4, right? 0, 1, 2, 3, 4. If I do substring of this P, 0 to 4, right? I'm going up to, but I'm not including the 4. So I'm not including this A. I'm not including that. So that would take a part of the string of CGTA. Okay? Hope you guys understand. CGTA. I'm taking a part of the string out of this whole string. So if I do substring 0, 4, right? I go up to, but I'm not including 4. Same thing if I do substring 1 to 4, right? So if I do substring, so 0, 1, right? So I'm starting 1, 1, 2, 3, 4. I go up to, but I'm not including 4, so I'm not including this A. So the substring of P of substring from index 1 to 4 will have GTA. GTA, the first A. I'm not including the last 4. That's what it's saying. Okay. So if you want to rule this out possibility, we restrict the definition to proper substrings, which is this. This is just saying that you are it's between 0 and the length. That's what it's saying. Okay, so they're using IJ to denote the substring. Okay, so that's just a mathematical definition. We use the okay, so if I is greater than J. Okay, so null string. So that's saying if you substring to itself, it just has the, like if I want a substring from index I to I, like 1 to 1, right? Well, there's nothing between 1 and 1, so that's null string. So that's nothing. Some special kinds of substrings, as it refers to the form 0 to I, which is prefix of p, or any substring of the form I to m minus 1 is a suffix. So for example, if we take the p to be the string of the DNA above, CGTAAA is a prefix of p. Oh, okay. And CGC is a suffix of p. Wait, what's the difference between prefix and suffix? Okay, so prefix, so they're saying anything of prefix of a string is starting from the index 0 and going up to the last index of the string, right? Suffix is just anything starting from the ith of which is any number between 0 and m minus 1. You're starting from I and you're substringing to the end of the string. So that's any number between 0 and then not including the last of this the end of the string, right? So that's why it's a suffix. Okay. The difference between a prefix and suffix is that one is starting from 0, the other one's starting from I. Okay. But either way, I could be 0 or 0. So, I mean, I don't know. Proper substring. Okay. No, there's no null and there's okay. So note that the null string is a prefix and suffix to any other string. To allow for general notions of the character string, we typically do not restrict the characters in T and P to explicitly come from well-known character sets like the ASCII or Unicode character sets. Instead, we typically use the symbol summation or the alphabet for which characters had come, since most document processing algorithms are used in applications where the underlying character set is finite, which we assume the size. Okay, so now we're going to talk about the string class. So remember, C-style string is an array of characters, right? Following the null character. C-style strings do not support complex string operations. The C++ template STL provides a complete string class. This class supports a bewildering number of string operations. We just list a few of them in the following. Let S denote the STL string object on which the operation is being performed, and let Q denote another STL string or a C-style string. So we have size returns the number of characters, empty checks if the string is empty or false otherwise. Operator returns the index at I of S without performing array bounds checking. Is the same thing. This is the same thing. Okay, insert inserts a string prior to the index in S and returns a reference to the result. Okay, append adds to the end of S, returns the result. Erase removes a character at the string. Okay. So this is substring. Returns a substring of length M starting at the index I. Okay. Oh, okay. Well, they're not even... Well, okay, so their definition of a substring is the length. Okay, they're not including the first and last index of where you're substringing to. So that's kind of different. Because for substring, for their substring, if I do start from 2 and I end at 4, then that means that I'm not ending at 4. I'm getting the length. So I'm gonna do 2 and I'm gonna go up to 4 places. That's their definition of a substring. That's STL's. I guess it could work, but I don't know. If Q is a substring of S, return the index to the beginning. Find, otherwise return N. Okay. C-style string contains a C. Okay. String is initialized. Okay, so by default, string is empty string. String may be initialized from another STL string or form a C-style string. If it is not possible, however, to initialize an STL string from a single character. STL strings also support functions that return both forward and backward iterators. All operations that are defined in terms of integer indices have counterpoints that are based on iterators. This STL string class also supports assignment of one string to another. It provides relational operators such as equals equals, less than, greater than, equals, which are performed lexicographically. Strings can be concatenated using plus, and we may append one string to another using plus equals. Strings may be input using the this is like greater, greater, less than. So this is using streams. The function get line reads the entire line from this input string and okay, the STL string class is also actually a special case of a more general templated class called the basic string, which supports all the string operations but allow its elements to be its arbitrary type, not just char. Okay, so this basically supports all string operations, not just character. Okay, it's a string of integers. Okay, so you could have a string of integers. Okay, this is just how it works. If you get size of this string, it's 16 because there's 16 characters in here. If you get at 5, it's asking the index at 5, which is 0, 1, 2, 3, 4, 5, which is F. F is the fifth. F is the fifth character. See? Yeah. S at 5, that's the same thing as at, which is the fifth character. So 0, 1, 2, 3, 4, 5. Okay, so that's F. Okay. S plus QRS. That's just gonna add QRS to the end of S. So you have A, B, C, D, F, G, L, P. After P, you add QRS. Okay, that's what it does. S equals just checks if the contents are equal to if this string is equal to this string. That is true. S dot find GHI. That's just this basically returns the index of the where you could find the characters GHI. So if basically searching through here, this is GHI, right? I'm trying to find GHI. So what is that? 0. I'm starting at front 0, 1, 2, 3, 4, 5, 6. 6. Okay, so that would return 6. Substring 4, 6. Okay, so basically their definition of substring is not the same thing as the definition of substring that I had. Their definition, there's no start and end index. For them, it's you start at 4, you go whatever characters long. So here, if I want a substring 4, 0, 1, 2, 3, 4, and they want to do 6 characters, you just do 1, 2, 3, 4, 5, 6. So that's all their characters, 4 to 6. Erase 4, 6. Okay, so erase 4, 6 is that just erases the characters from 4 to 6. So 0, 1, 2, 3, 4, 5, 6. So I'm gonna erase 6. Wait, let me see. 6 characters, right? Starting from 4, I think. So let me see. A B C D A B C D. Okay, so here 0, 1, 2, 3, 4. I'm gonna erase 6 characters. There's 1, 2, 3. Wait, 1, 2, 3, 4, 5, 6. So that takes out all these. These are now gone. Okay? Erasing that. So now I have A, B, C, D, and then what is it? K, L, M, N, O, P. Yeah, so that's that. Okay, insert. I insert before the index of 1. Insert these characters before the index of 1. So if I want to do that, I have to insert it right before here. So that would be X, 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 X. Okay? You get that. S plus equals to XY. That just adds it to the end of XY. There's a fly near me. Okay. Append add just adds the to end. With the exception of find, we discuss all the characters are implemented by representing the string. So one thing about strings is that sometimes you want to know the difference between two strings. And what I mean difference is that one string is a subsequence of another string. And what does that mean? That basically means if you take the characters out of one string, it's exactly the same characters on another string. So AAG is a subsequence of this, because if you take the characters of some of the characters, you can take A out from here, these two A's out, these three A's out actually. If you take these two A's, if you take these two A's out and you take this A out and you could take this G out, you get AAG. So that sometimes you want to find the subsequence of X. And the problem we address here is the longest common subsequence. And this is basically you're given two strings over some alphabet, ACGT, and you're trying to find the longest string S that is the subsequence of both X and Y. One way to solve the longest subsequence is to just go through every single subsequence of x and take the longest one. That is also subsequent to y. Since each character of x is either in or not in a sequence, there are potentially to the n different subsequences of x, thus of which requires O of m time to determine whether it is a subsequence of y. Thus this brute force yields an exponential time that runs O of 2 to the nm, which is inefficient. But you could solve it using dynamic programming. So the components of a dynamic programming solution. The dynamic programming technique is used primarily for optimizing problems where we want to find the best way of doing something. You could apply the dynamic program technique in such situations if the problem has certain properties. Simple subproblems, there has to be some way of repeatedly breaking the global optimization problem into subproblems. There should be a simple way of defining subproblems with a few indices. Subproblem optimization, the optimal solution to the global problem must be composed of optimal subproblems. Subproblem overlap, optimal solutions to unrelated subproblems can contain subproblems in common. So applying dynamic program to longest common subsequence. Longest common subsequence. So you're given two strings, and they each have different lengths, and you're trying to find the longest common subsequence of both x and y. Since they're character strings, they have a natural set of indices with which you could define subproblems for x and y. So let's define a subproblem. To compute the value L of ij, which is the longest subproblem of ij, we will use to denote the longest string that is a subsequence of both of x and y, right? These are strings. These are strings. Don't mistake these for like math symbols. These are strings, okay? So we're gonna rewrite L in terms of subproblem solutions, depending on the cases. So basically, we're gonna break this up into small subproblems, and here's what they're saying. Okay, so we're going to have a definition that tells us the optimal subproblem solution. So if I have here longest longest subsequence, right? Longest common subsequence, right? So that means they had, I told you they share the same thing, right? So for longest subsequence of 8, 10, what is that? So that's at index 8 for x, which is right here, this t, right? And then the index 10 for y. So what is that here, this g? So longest subsequence for 8 and 10 for these two strings for x and y is 5, because the common characters you have, well, you have c, which is 1, you have t, which is 2, you have these two a's, which is 4, right? 4, because you have these two a's, 4, and then you have a common t, which is 5. And that's a common between 8 and 10. 8 and 10 for x and for y 10. So they're saying Lij is the optimal subproblem for the longest common subsequence for I and 10, which is for 8 and 10, right? For x and y. So that's for this. Also for, in this case, the longest subsequence for x and y starting from for the index 9 and 9, well, we're going to end at 9, 9, right? So x, the longest sequence for 9, for x, we start at 9, and longest subsequence for y, we end at for 9 for y, right? What is that? Well, we have c, which is 1, we have t, which is 2, we have a, which is 3, we have a, which is 4, we have t, which is 5, and then we also include the last one, because we're also including 9, right? We have a, which is 6, right? So we have 1, 2, 3, 4, 5, 6, right? So that's why 9, 9 is 6. And 8, 10, which was this right here, is 5, right? 8, 10 was 5. So because if you look at 8 from here, 8, and then 10 is g, right? 8 is t, 8 is x, right? 8 is the index for the last number where index for x, 10 is the last index for y, right? So for 8 and 10, what is that? So we have C, we have T, we have A, which is 4. We have T, right? But then for 10, we don't have any, we don't have this A because we're going from 8 to 10, right? So that means there's nothing else from the last two that shares for 8 with 8 with T and G. Nothing else from here shares, so that's why it's 5. So 8 and 10 is 5, right? Because this A, we don't include it because our last character for X is 8, which is T, right? So we can't include the A. So that's why it's for 5 for this one. So these are the two cases for the longest common subsequence algorithm for xi not equal to yj. Note that the common algorithm stores only the lij values, not the matches. So xi is equal to yj. In this case, we have a match between the last character for I and the last character of j for x and y, right? We claim that this character belongs to the longest common subsequence, x and j. To justify this claim, let us suppose that it is not true. There has to be some longest common subsequence, xi, xi2, xik, which is equal to yj1, yj2, up to yjk. So if xik is equal to xi, or jk is equal to yj, then we have the same sequence by setting I to k equal to I and j of k equal to j. Alternatively, if xjk is not equal to xi, then we can get an even longer subsequence by adding xi to the end. That's the longest common subsequence of x0 up to I and y up to j ends with xi. Therefore, we set I and j equal to this if xi is equal to yj. Okay? So, basically, what are they saying here? So, let me try to explain this. So, if we have the same match for the last character for x and y, right? We can claim that this character belongs to the longest common subsequence of the last two characters, right? Because, like based on our previous case right here, if we know the, let's say T and T, right? Let's say we're going from 8 to 7, right? For 8 to 7 for X and 7 to 7, right? We could claim that our T is part of the longest common subsequence, right? I mean, it makes sense. It's part of the string that we're going up to, right? So that's what they're saying here. We could claim that this character belongs to the longest common subsequence. To justify this claim, so this whole thing is just a justification. They suppose it's not true, and then there has to be some longest common subsequence. Alternatively, if j is then we get a longest by adding. Okay, so they're saying that there has to be some longest common subsequence where the characters are equal, right? Like the characters for each of these characters have to be equal, right? They're common, right? That's what this is, right? Here it's saying that if the previous two are equal, so like from here and here, right? Or if let's say the last two are equal. So here what they're saying is that if the last characters for your sequence from here to here, right? From, let's say we're going from 8 to 7, right? If the character from the beginning and to the end are equal. That's what they're saying here. Like, because the character beginning is xi at 1, right? Character at end is xik, right? If they're equal, or the y's are equal, right? Then we get the same sequence. Right? We get the same sequence if we set them to equal each other. Right? We get the same sequence if the last two are equal, right? If this and this, if the beginning and end are equal, you have the same sequence. So alternatively, if they're not equal, right? If whatever your value at what do they say? JK. What is JK? JK is the let's see, where is it? Oh, right here. Okay, so if x at jk is not equal to x at I, so what does that mean? So if whatever your value at your beginning is not equal to the one at your end, then we can get an even longer subsequence by just adding the whatever our previous one to the end. That's the longest common subsequence of aj, a at a, and j ends with x at I. So here they're saying is that you could take the first character, or no, not first, your last character. You could take the last character that you have and add it to the end if they're not equal, right? And that would be the longest common sequence would end with it. Okay? If you take the last character of x and you add it to the end, if the beginning and end are not equal, right? Then your longest common subsequence would be whatever that ends, whatever value that you ended at your last character for x. So whatever value ended, so if at t, the last character would be t, right? If we go 8 for x 8 and y at 7, right? Well, they're saying if they're not equal, but let's say they're not equal. Okay, well, they are equal in this case, but basically if they're not, you could take that your last character for x and you could append it to the end, and that would be your common subsequence as well. So therefore we could set our array of what we're saying that the longest subsequence of I and j is actually the previous one plus 1 if your values at your last characters are the same. Like if your last characters are the same for I and j. So like if your last character for this one is the same as this one. Now if they aren't the same, in this case you cannot have a long common sequence that includes both of them, and that is we have a common sequence that ends with different ones, right? Xi or yj, that means they're different, right? But not both. Therefore we have to set, you could set them to have the maximum of your array at your previous sequence of j, which is I'm guessing it's okay, so your previous sequence and your previous sequence minus 1. So the maximum subsequence, you can't take the one and you append it to the end. You could take the maximum of your previous ones and see if that and that would be whatever is at your current position, right? So in order to make both of these equations make sense in the boundary cases when I is equal to 0 or j equals 0, you could assign them in the beginning to start at 0, and then you could figure it out while you loop through it. For j is -1 and then up to n minus 1. So here's the definition. Definition of it, Lij satisfies subproblem optimization since we cannot have a longest common subsequence without having longest common subsequence for the subproblems. Also uses subproblem overlap because a subproblem solution Lij can be used in several other problems, namely the problems Li plus 1j and Lij plus 1 and Li plus 1j plus 1. Turning this definition of Lij into an algorithm is actually quite straightforward. We initialize them into a 2D array. If the boundary case is starting at 0, 0. Yeah, for I is your -1 up to n minus 1. Okay, so for I they're gonna start at -1 to have the value 0. For j they're gonna -1, and then you iteratively build up values until you have the length of a longest common subsequence of x and y. And here's a pseudocode. So for strings x and y with n and m elements respectively, you start I equals 0 and you go up to it. The length of ij of the longest common subsequence of both of them is this, and the length of j is that. So they're going to initialize the whole array to have value 0 first. Then they're going to initialize the second array, the second column, I'm guessing, because it's 2D array, right? Have all zeros. They're gonna loop through it and loop through it if the last value at your sequence, right, xi, which is the last value, your last character, is the same, then your longest common subsequence is just your previous one plus 1 of I minus 1 plus 1, right? Because that's your... Remember, that means if they're the same, that means you could take the last one and append one, right? We talked about that. That's what they were talking about. Otherwise, you take the maximum of your previous ones. That's what they're saying here. And then you return the array. So this is a way of dynamic programming. The running time of the algorithm is easy to analyze. This is 2 nested for loops, and it goes n and m times. It requires O of 1. This runs n and m. Thus, a dynamic program can be applied to the longest common subsequence in order to improve significantly over the exponential time brute force. So, algorithm LCS computes the length of the common subsequence by storing m, but not the subsequence itself, as shown in the following proposition. A simple post-processing step can extract the longest common subsequence from the array L returned by the algorithm. Given a string x of n characters and a string y of m characters, we can find the longest common subsequence of x, y, and n log O of n m time. Algorithm LCS computes L n minus 1 and m minus 1, the length of the longest subsequence, and O of n m time. Given the table of values, you construct it. This is straightforward. One method is to start from n and m and work backward through the table, reconstructing a longest common subsequence from the back to the front. Any position, we can determine whether xi is equal to yj. If this is true, then we can take xi as the next character in the subsequence for the previous one, and then if it's not equal, we can move the largest value to that. We stop the boundary cell at -1 and j and -1. So this constructs a long subsequence n plus 1 time. So yeah, that's what they do here. And that gets the longest common subsequence. The algorithm for constructing a longest common subsequence of the array. Alright, so let's talk about pattern matching algorithm. Alright guys, now we're going to talk about pattern matching. So a classical pattern matching problem is where you're given a string and you try to find whether another string is a substring of it, right? And that is just by trying to find whether, when I say a substring, is like part of the string is a part of another string, right? Well, this is a classic pattern matching problem, and this is the exact computation of how the find function works in STL's string interface, where you want to find all the indices where the substring of one string is a matches another string P, right? So here we're going to talk about 3 pattern matching algorithms with increasing level of difficulty. So one pattern matching algorithm is called the brute force algorithm design pattern, which is basically you search every single possible outcome, right? And in applying this technique, it's basically it's a powerful, and it's a way like you have something you wish to search for, and when you wish to optimize some function. So in applying this technique in a general situation, we typically enumerate all possible configurations of the input involved and pick the best. Okay, this is called brute force pattern matching, and we derive what is probably the first algorithm that we might think of for solving the pattern matching problem. We simply test all the possible placements of the relative P relative to T. This algorithm is quite simple. So in finding all the possible outcomes of this, checking if a substring of n characters is a substring of another, right? If T is a substring of P, right? Start at the first, the output is that we want to start in the start index of the first substring, right? This is the output. So what do? You loop through it, okay? So what do you loop through? Well, you loop through the length of the difference between the two lengths of the second P and the first P. Why do you do that? Well, because if we want to find the substring of T of P, checking if there's the substring of the first one matches the second one, well, we know that P must be larger than T, right? The size, the length of the T, the size of each number of characters of P must be greater than T. So if we subtract the number of characters for each candidate index in T, right, with n characters minus m, that will show us, that will tell us the difference between the size, the length of each of the two strings, and that helps you. Why? Because then you could loop through. You could loop through, right? And basically this is going to loop through starting from J, 0, while it's less than the length of your second string, right? You want to check every single length of the second string, and basically you're going to get each position of what you're looping through in the beginning, add it to that, and check if it's equal to P of J. And if it is, then we add 1, right? Then once the index is equal to M, which is the size of the characters, then we return it. So how does this work? I'll just show you how this works. So let's say I have the string str, and this is T. And let's say I have the string let's see, str, okay, str. So what do? Right, we start at I, which is 0. I is 0, okay? And then we take n minus n, okay? Well, what's n? N is n characters. P is m, right? Okay, wait. So, so they're actually assuming that you're trying to find the substring of the other one. So, let's assume T is str, and P is str, right? Because we know that T is going to be greater than the size of T is going to be greater than the size of P, right? So we take n minus m, right? N is the size of T, so n is 6. And what's P? P is 3, right? So we have 6 minus 3, so which is 3. So I'm gonna loop through I to 3, right? J is gonna start at 0. While 0 is less than M, what is M? M is this, my bad. M is P, right? While J is less than M, while J is 0 is less than 3, right? We're going to take T of 0 plus 0. 0 plus 0. Okay? T of 0 plus 0. That's 0. So T of 0 is that's this S. Is that equal to P of S? If it is, then we add J by 1. So it is. So we're going to add J plus 1. So that's J plus 1, right? So now that increments J by 1. 1 is still less than 3, right? 1 is still less than 3. So what do? We check. We take I. What's I? I is 0. I is still 0, right? I is still 0, okay? So we're going to do add 1 plus I. 1 plus 0 is 1. T of 1. Is T of 1 equal? Is T of 1, which is T. That's this T. Is this equal to J, to T of J? What is T of J? This T. Yes, it is. So we're going to add 1, so that becomes 2 now. Okay? 2 less than 3. Yes, 2 is less than 3. 2 plus 0, because I is 0, is 2. Is that equal to P of 2? No, yeah, P of 2. Is 2 equal to 2? So, 0, 1, 2. Is this R equal to R? Yes, it is. So this becomes 3. Now they're equal. Alright, now they're equal. So now, now 3 is equal to this M, 3, right? So then this while loop stops. Why? Because there's a less hand sign, right? 3 is not, because 3 is 3 less than 3? No, it's not, alright? So then this is gone. Now is 3 equal to 3? Yes, it is. So we're going to return I. So I is going to be 0. So that returns the substring of this. Okay? That's the index of the substring, which it starts at I, 0. Okay? So now let's say if it never worked. If it never worked, then basically This loop is basically just looping through and just going through the difference of the size, because that's all the possible combinations, right? Then this loop is the checking if it's equal to if your index where you're at is equal to the index of the string. And once it is, it adds 1. Why does it add 1? Because they want to check if it's all of it's equal. They want to check if the string at the position is equal to it. If all the strings are equal, so then they add 1. Once they if in the end they are actually equal, then they return. That's what they do. Okay, we're going to talk about performance now. The brute force pattern matching algorithm could not be simpler. It consists of 2 nested for loops, with the outer loop indexing through all possible starting indices of the pattern in the text, and the inner loop indexing through each character of the pattern, comparing it to its potentially corresponding character in the text. Thus, the correctness of the brute force pattern matching algorithm follows immediately from this exhaustive search approach. The running time of brute force pattern matching in the worst case is not good. However, because for each candidate in T we can perform up to m character comparisons to discover that P does not match T at a current index. Referring to the code, we see that the outer loop executes at least n minus m plus 1 times, and the inner loop is executing at most m times. Thus, the running time of the brute force method is n minus m plus 1 times m, which is simplified as O of nm. Note that when m is equal to n over 2, this algorithm has quadratic running time, O of n squared. So let's say we take the string P equal to this, and then the T we're given is that. So we illustrate the execution of the brute force. What do? We first subtract the size of it, right? So what is the size? Well, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Well, yeah, okay. So basically what they're going to do is they're going to loop through from A, B, C, A, B is the second string, and they're going to compare. Okay, they compare it with each other. Compare this to that. Compare it, right? Compare until you get 11 comparisons. And then after the brute force method, the algorithm performs 27 character comparisons indicated with Roman numerals. Numeric labels. Okay, now let's talk about another another pattern matching. So you might think that you have to go through every single character to locate it as a substring, but that's not always the case. There's another pattern matching algorithm called Boyer-Moore, which we study in this section. You can avoid comparisons between P and the sizable fraction of the characters in T. The only caveat is that whereas the brute force algorithm can work even with the potentially unbounded alphabet, the BM algorithm assumes that alphabet is a fixed finite size. It works the fastest when the alphabet is moderately sized and the pattern is relatively long. Thus, the BM algorithm is ideal for searching words in a document. In this case, we describe a simplified version of the algorithm. Main idea is to improve the running time of the brute force by adding 2 potential time-saving heuristics. One is looking glass heuristic. When testing a possible placement of P against T, begin the comparison from the end of P, then move back to the front. Character jump heuristic. During the testing of the possible placement of P against T, a mismatch of a text character with the corresponding pattern character P to J as follows. If the character C is not contained anywhere in P, then shift P immediately past T of I, for it cannot match any character. Otherwise, shift it until an occurrence of the character C in P gets aligned with it. So all they're saying is they're going to jump around. Once you realize a character is not equal to it, the first character that is not equal to it, just jump around and shift it past it. Otherwise, shift it until the occurrence of C actually aligns with it. So we formally use the heuristics shortly, but at an intuitive level they work as an integrated team. The long looking glass heuristic sets up the other heuristics to allow us to avoid comparisons between P and whole groups of characters in T. In this case, at least, we can get the destination faster by going backwards. For if we encounter a mismatch during the consideration of P at a certain location in T, then we are likely to avoid lots of needless comparisons by significantly shifting P relative to T by using character jump heuristics. A character jump heuristic pays off if it can be applied early in the testing of each placement of P against T. So now, therefore, let's get down to the business of how do we define the character jump heuristics, how they're integrated in the string pattern matching algorithm. To implement this heuristic, we define the function last C that takes the character C from the alphabet and characterizes how far away we must shift the pattern P if a character is equal to C is found and does not match the pattern. In particular, we define last E as if C is in P, last C is the index of the last rightmost occurrence of C in P. Otherwise, we conventionally define last C equal -1. If the characters can be used as indices in arrays, then the last function can be easily implemented as a lookup table. We'll leave the method for computing this task later on as an exercise. This last function gives us all the information we need to perform the character jump heuristic. So here's the algorithm. So we have the string T with n characters and P with m characters. We start at the index of the first substring of T matching P, or an indication that P is not a substring of T. So what do? Computing last. We set I equal to the last character of the pattern P, right? And we set J to equal to the index of the last character of P also. Then we're going to repeat, right? If it's equal to it, then we set J, and J is equal to 0, then we return it, right? That means there's a match. This is basically saying, based on the last two indices, right, if of each one, if the first string at that index is equal to it, then we return it. Why? Because they're a match. Okay. Otherwise, we decrement. We're going to decrement both of the indices. Okay. Now, if they're not a match, then we're going to add by the size of the second string P, right? P has a size of m characters. So then we're going to add that by I. Then we're going to subtract the minimum. The minimum of J. What is J? J is basically the other index of the counting from the back, right? It's the index for the P pattern, right? We subtract the minimum of this plus and 1 plus the last of T of I. What is T of I? T of I is the index starting from last for T. Okay? So we're going to plus last of T of I. So what is last of T I? T of I last is the... Did they explain it? Oh, is the index of the rightmost occurrence of C. Okay? It's the index of the rightmost occurrence of C. So, yeah, that gets that. And then we subtract 1 by J. And then we do this until I is greater than n minus 1. Alright? Then that means there's no string matching. So here's how it works, okay? We have these two strings, right? A and B. Okay? Because they're not equal. We know they're not equal. So what are we going to do? Okay, we're going to do I is going to equal to 1 plus last of T of I. What is that? Last of T of I is the jump of T of I. So that's going to be, what is that? 0, 1, 2, 3, 4? I think it's 4. Wait, that doesn't make sense. Okay, well, it's going to subtract these two and find the minimum. That's what it's doing. I kind of don't understand what they're doing here, but that's basically what it's doing. Last jump of the algorithm, we will let IL equals the last T of I. Okay, so that shifts it right. So if you execute the algorithm, it looks like this. C's last function is going to get you 5, 4, 5, 3, -1. The correctness of the BM pattern matching follows from the fact that each time the method makes a shift, it is guaranteed not to skip over any possible matches. This is because last C indicates the last occurrence of C in P. The worst case running time of the algorithm is this. Namely, the computational last takes O of m plus sigma time, and then the actual search for the pattern takes nm time. Same thing as a brute force algorithm. Okay, the worst case is unlikely for the English case. Okay, okay. So here's a C++ implementation of it. We have the text, and then we have the thing we're searching for, right? See if it's pattern. We get the size of the two, and we get the index of the last character for our P, right? The one that we're trying to find, the pattern, right? While it's greater than, if it's greater than n minus 1, that means pattern is no longer is, if the pattern is longer than text, then that means there's no match. Otherwise, we get the size of the other one of P, okay? And we do a do while. Excuse me. Do while if the pattern is equal to the text, we found a match, to return it. Otherwise, you subtract it. Otherwise, we add them together and find the minimum of j and 1 plus the last index of text of I. This does the character jump, and then we do j equals n minus 1, and then after that we return -1 if there's no match. And here's the function that you build the last function. This last just takes you the last character that was part of it. So here they're trying to build it. So they build it by creating a vector, and they're going to initialize all of them to have -1, and then they're going to implicitly cast to ASCII code. I don't know why. Why are they doing that? Okay, whatever. Algorithm express two static functions. Method bmmatch performs the matching and calls for auxiliary function. Build last function to compute the last function expressed by an array index by the ASCII code of the character. Method bmmatch indicates the absence of a match by returning the conventional value -1. Okay, so we already have been presented a simplified view of the Boyer-Moore algorithm. The original BM algorithm achieves running time of that by using an alternative shift heuristic to the partial matching text string whenever it shifts the pattern more than the character jump heuristic. This alternative shift heuristic is based on applying the main idea from the Knuth-Morris-Pratt pattern matching algorithm, which we'll discuss next. Okay, so now we're going to discuss about the Knuth-Morris-Pratt algorithm. So the worst case of the brute force and BM matching algorithm is based on specific instances of the problem. Such that given in this example, you should notice a major inefficiency. We may perform many comparisons while testing a potential placement of the string against the text, yet if we were to discover a pattern character that does not match the text, then we throw away all the information gained by these comparisons and start all over again with the scratch of the next incremental placement of the pattern. This new algorithm, a KMP algorithm discussed, avoids this waste of information, and doing so achieves a running time of O n plus m, which is optimal for the worst case. That is the worst case of any pattern matching algorithm. Will have to examine all the characters in the text and the characters of the pattern at least once. So failure function. The main idea of the KMP algorithm is to pre-process the pattern string so that you compute a failure function that indicates the proper shift of P so that to the largest extent possible you can reuse previously performed comparisons. Specifically, the failure function fj is defined as the length of the longest prefix of P, that is a suffix of P of I up to j. We also use a convention that f of 0 is equal to 0. Later we discuss how to compute the failure function efficiently. The importance of the failure function is that it encodes repeated substrings inside the pattern itself. So consider the string of this. String P equal to AB, A, C, AB. From the example, the KMP failure function f of j for the string P is shown in the following table. So if the pattern matching incrementally processes the string, comparing it to the pattern string P. Each time there is a match, we increment the current indices. On the other hand, if there is a mismatch, we have previously made progress in P, and then we consult the failure function to determine if the new index in P, where we need to continue checking P against T. Otherwise, there is a mismatch at the beginning, and we simply increment the index for T, and we keep the index variable for P at its beginning. We repeat this process until we find a match of P in T, or the index for T reaches n. The length of T indicating that we did not find a pattern. So we construct a failure table. We start index at I equals 0, j equals 0. We loop while I is less than n. What is n? N is basically the size of T, right? Then we check if they're equal. If they are, then we subtract 1 by and then if j is at the end, if j is at the end of the last index, then we return it. Okay, we return I minus n plus 1 because that's if it's at the end, that means subtract, that's the how far it is from the beginning string, because you subtract by the length, right? And that'll be the starting of where the match was, so that returns that. Otherwise, you increment, right? You're gonna increment I and j. Okay. Otherwise, if there's no match, we advance p, and then j is gonna be the index just after the prefix of p that must match. Then we add I by 1. The main part of it is the while loop, which performs a comparison between a character in t and a character in p after each iteration. Depending on the outcome of this comparison, the algorithm either moves on to the next characters in t and p, consulting the failure function for a new candidate character in p. Starts over with the next index in t. The correctness of this algorithm follows from the definition of the failure function. Any comparisons that are skipped are actually unnecessary, for the failure function guarantees that all of the ignored comparisons are redundant, and they would involve comparing the same matching characters over and again. So here are the comparisons. This illustrates the example of it. Okay, here's a performance. If they're equal, it increases 1, it doesn't change. J, okay, so if they're equal, then I does not change, and K increases by 1 at least. Yada yada, this is an addition. If U does not equal, then J increases by 1, which does not change. Thus, at the iteration, do while, so it's at most 2 of n. Okay. To construct the failure function, we use the method below. Bootstrapping and process the same thing as KMP. We compare the pattern to itself. Each time we have 2 characters in match, we set it. Yeah. So then once we have that, set I equals 1, J, okay. If you have a match, yep. So that's setting that. Here's a C++ implementation of it. We get the size of the text, size of the pattern. Check if the compute fail function. Then we have the I start at 0, J start at 0. We loop through it. We check if there's a match. If there is, we found a match. We increment it. Otherwise, we set J equals the fail. Okay, it's the fail array, and then -1 else ++. Okay, so then in the computing the fail function, this is what we do. We set the fail function start at 0. M is going to equal to the pattern dot size. J is going to start at 0. I is going to start at 1. We're going to loop through it. Check if the pattern matches. If it matches, we set the fail at I is the array at I is going to equal to J plus 1, because that means that the patterns match, right? Then once it matches, we I and J plus 1. Then also if we check if J is greater than 0, J is equal to fail J minus 1. Else fail I is equal to 0. I plus plus return fail. Okay. Oh, excuse me. Alright guys, we're going to talk about text compression and greedy method. So we're going to consider an important text processing task called text compression. In this problem, we're given a string X defined over an alphabet, such as an ASCII or some set. We want to efficiently encode X into a small binary string Y, using only the characters 0 and 1. Text compression is useful in any situation where we are communicating over a low bandwidth channel, such as a modem line or infrared connection, and we wish to minimize the time needed to transmit our text. Likewise, text compression is often useful for storing collections of large documents more efficiently, in order to allow for fixed capacity storage device to contain as many documents as possible. So the method for text compression is the Huffman code, and the standard encoding schemes such as the ASCII and Unicode systems use fixed binary strings to encode characters. So a Huffman code, on the other hand, uses a variable length encoding optimized for the string X. The optimization is based on the character frequencies, where we have for each character C a count FC of the number of times C appears in the string X. The Huffman code saves space over a fixed length encoding by using short code word strings to encode high frequency characters and long code word strings to encode low frequency characters. So to encode the string X, we convert each character in X from its fixed length to its variable length word code. And we concatenate all these codes together to produce the encoding Y for X. In order to avoid ambiguities, we insist that no code word in our encoding is a prefix of another code word in our encoding, so this is called prefix code. It simplifies the decoding Y in order to get back X. Even with this restriction, the savings produced by a variable length prefix code can be significant, particularly if there is a wide variance in character frequencies, as is the case for natural language text in almost every spoken language. So Huffman-Tim's algorithm for producing an optimal variable length prefix code for X is based on the construction of the binary search tree T that represents the code, each node in T, except the root represents a bit in a code word, with each left child representing 0 and each right child representing 1. Each external node, V, means children without nodes without children, right, associated with a specific character, and the code word for that character is defined by the sequence of bits associated with the nodes in the path from the root of T to V. Each external node V has a frequency, f of V, which is simply the frequency in X of the character associated with V. So in addition, we give each internal node V in T a frequency, f of V, that is the sum of the frequencies of all the external nodes in the subtree rooted at V. So here's all the frequencies, right? So we give them numbers. Here's an example for the string: a faster runner will never be afraid of the dark. Frequency for each character X, and then a frequency for Huffington tree for a string X. So then now we have frequencies. So for A, what was that? 1, 2, 3, 5, I think. 1, 2, 3, 4, 5, and then frequency for B. We have one of these. Yeah, where is it? 1. 1B. Yeah, and then you have all these frequencies for each string, right? And then the code for character C is obtained by tracing the path from the root of T to the external node where C is stored, associating a left child with 0 and the right child with 1. For example, the code of A is 0, 1, 0. So the code of A is going to be 0. A left child is 0, the right child is 1. So 0, 1, 0. Right, and then the code of F is, where's F? 0. No, it's, left child is, wait. I don't get it. Wait. 1, 1, 0. Okay, well, why is it 1, 1, 0? Okay, so wait, let me see. The code is a 0, 1, 0. I know that. The code for a character C is obtained by tracing the path from the root of T to the external. Oh, from the root of T. Okay, so each, what was it? So left child is 0, right child's 1. So for F, we're gonna go 1, 1, 0, 0. Yeah, that's why F is 1, 1, 0. Well, my fault. F is 1, 1, 0, 0. Yeah, so 1, 1, 0, 0. Okay. A is 0. So A, you gotta go from 0, 1, 0. Okay, so that's how it works. How this works. Okay. I don't care what these numbers are. 19. Guessing you. Oh, you add up the frequencies together. Oh. Okay, 5 plus 5, 10. Okay, so 7, 12. Oh, okay. So that's how this works. Okay. So you keep up the frequencies for each letter, and then you add them up for the root for each parent node, right? So 1 plus 1 is 2. So yeah. So then if you want to traverse for the code, you would just go left child is 0, right child's 1. So yeah. Okay. So Huffington code algorithm, it begins with each of the D distinct characters of the string X in code being the root node of a single node binary tree. The algorithm proceeds in a series of rounds. In each round, the algorithm takes the two binary trees with the smallest frequency and merges them into a single binary frequency. Single binary tree. Repeats this process until only one tree is left. Each iteration of the while loop in the Huffman's algorithm can be implemented in log D time using a priority queue represented with a heap. In addition, each iteration takes two nodes out of queue and adds one in, a process that is repeated d-1 times before exactly one node is left in queue. Thus, the algorithm runs O of n plus d log d time. Although a full justification of this algorithm's correctness is beyond our scope, we note that its intuition comes from the simple idea any optimal code can be converted into an optimal code in which the code words for the two lowest frequency characters A and B differ only in their last bit. Repeating the argument for a string with A and B replaced by a character C gives the following. So Huffington's algorithm constructs an optimal prefix code for a string of length n with D distinct characters in that time. Okay, so yeah, compute the frequency of each character. So we saw that using a priority queue. For each character is the thing, create a binary search tree storing C, insert it into with this key F as C. While the queue is without size greater than 1, get the minimum, remove the minimum, get the minimum again, remove the minimum, create a new tree, the left subtree with that, then return queue to remove minimum. Okay, let's talk about greeting method. Like Huffman's algorithm for bidding and optimal encoding is a great example of an algorithm design pattern called the greedy method. This design pattern is applied to optimization problems where we try to construct some structure for minimizing the maximizing some property of that structure. General formula for a greedy method is almost as simple as a brute force method. In order to save us a given optimization problem using the greedy method, we proceed by a sequence of choices. The sequence starts from some well understood starting condition and computes the cost for that initial condition. The pattern then asks that we iteratively make additional choices by identifying the decision that achieves the best cost improvement for all the choices that are currently possible. This approach does not always lead to an optimal solution, but there are several problems that it does work for, and such problems are said to possess the greedy choice property. This is the property that a global optimal condition can be reached by a series of locally optimal choices. That is, choices that are each the current best from among the possibilities available at the time, starting with from a well-defined starting condition. The problem of the computing an optimal variable length prefix code is just one example of a problem that possesses the greedy choice property. Okay, so, oh, wait, is that it? Okay, we're going to go over tries now. Ooh. Okay, tries are going to be something. Well, I'm going to get a drink of water and then we'll go over. Alright guys, we're going to talk about tries now. So, the pattern matching algorithm presented in the previous section sped up the search in a text by processing the pattern to compute the failure function in the KMP algorithm or the last function in BM algorithm. In this section, we're going to take a complementary approach, namely we're going to present strings searching algorithms that pre-process the text. This approach is suitable for the applications where a series of queries is performed on a fixed text so that the initial cost of pre-processing the text is compensated by a speed-up in each subsequent query. So a trie is a tree-based data structure for storing strings in order to support fast pattern matching. So the main application for a trie is in information retrieval. Indeed, trie comes from the word retrieval. In an information retrieval application such as searching for a DNA sequence in a database, we are given a collection of S of strings and we are defined using the same alphabet. So the primary query operations that tries support are pattern matching and prefix matching. The latter operation involves given a string X looking for all the strings in S that contains X as a prefix. Standard tries. Let S be a set of S strings in the alphabet such that no string in S is a prefix of another string. A standard trie for S is an ordered tree T with the following properties. So basically each node except the root is labeled with a character. The ordering of the children of an internal node is determined by the conical ordering of the alphabet. So that means that like the ordering of the children are based on some ordering of the alphabet, right? If T has S external nodes, that means the nodes outside that have no children, right? Each associated with the string of S, such that the concatenation of the labels on the nodes on the path from the root to an external node V of T yields a string of S associated with V. So that's just saying that whatever S external node that you have, if you go through the path from the root to an external node, it gives you the string associated with it, right? So that's what this is saying. So thus a trie represents the string S with paths from the root to the external nodes of T. Note the importance of assuming that no string in S is a prefix of another string. This ensures that each string of S is uniquely associated with an external node of T. We can always satisfy this assumption by adding a special character that is not in the ordinary original alphabet at the end of each string. So an internal node is a standard trie that can have anywhere between 1 and D children, where D is the set of the alphabet. There is an edge going from the root R to one of the children for each of the characters that is first in some string in the collection S. In addition, a path from the root of T to an internal node V at depth I corresponds to an ith character prefix of the string. In fact, each character C that follows the prefix X in a string of the set S, there is a child of V labeled with children C. Right? In this way, a trie concisely stores the common prefixes that exist among a set of strings. So if there are only two characters in the alphabet, then the trie is essentially a binary tree with some internal nodes possibly having only one child. That is, it may be an improper binary tree. In general, if there are D characters in the alphabet, then the trie will be a multi-way tree where each internal node has between 1 and D children. In addition, there are likely to be several internal nodes in a standard trie that have fewer than D children. For example, the trie has several internal nodes with one child. We can implement a trie with a tree storing the characters at its node. So here's what a trie is. Like if you go through the root, you get to the string, right? If you go B, E, A, R. So the standard trie for the bear. So bear is B, E, A, R. Bell, B-E-L-L. Bid, B-I-D. Bull, buy, B-U-Y. B-U-L-L. S-E-L-L. S-T-O-C-K. S-T-O-P. Yeah, stop. So that goes that way. Okay, so that's that. So the proposition: a standard trie collection of S strings of total length n from an alphabet of size D have the following properties. Every internal node of T has at most D children. T has S external nodes. The height of T is equal to the length of the longest string in S. Number of nodes of T is O of n. Okay. So worst case, it occurs when no two strings share a common non-empty prefix. That is except for the node root. All internal nodes have one children. Trie T has a set S of strings that can be used to implement a dictionary whose keys are the strings of S. Namely, we could perform a search for string X by tracing down the root. If this path can be traced and terminates at an external root, then we know X is in the dictionary. For example, if you trace the word ball, it terminates at an internal node, then X is not in the dictionary. But the path bet cannot be traced, and the path for B ends at an internal node. Okay, so that's what they're saying. So that's how you trace it. It is easy to see the running time is O of DM, where D is the size of the alphabet. For some alphabets, we may improve the time spent to O of 1 log of D by using dictionary of characters, implementing a hash table or search table. From discussion above, it follows that we can use a trie to perform a special kind of pattern matching called word matching, where we want to determine whether a given pattern matches one of the words of the text exactly. Word matching differs from standard pattern matching since the pattern cannot match an arbitrary substring of the text, but only one of its words. So using a trie, word matching for a pattern of length m takes O of dm time, where d is the size of the alphabet independent of the size of the text. If the alphabet has constant size, as is the case for text in natural languages, in DNA, a query takes O of m time, proportional to the size. A simple extension of this scheme supports the prefix matching queries. However, arbitrary occurrences of the pattern in the text, for example, the pattern is a proper suffix of a word that spans two words, cannot be efficiently performed. To construct a standard trie for a set S of strings, we can use an incremental algorithm that inserts the strings one at a time. Recall the assumption that no string of S is a prefix of another string. To insert a string X into the current trie T, we first try to trace the path associated with X in T. Since S is not already in T and no string in S is a prefix of another string, we stop tracing the path at internal node V of T before reaching the end of X. We then create a new chain of the node descendants of V to store the remaining characters of X. And so to do that, the insertion time is O of dm, where m is the length of the X and D is the size of the alphabet. Thus constructing the entire set takes O of dn time. Okay, so they're basically saying you're going to use a hash table, I guess, or a map or whatever, a dictionary, what do they call it? And they're basically going to put all these things in there. So for B-E-A-R, right? So B-E-A-R, they're going to put this in here. for starting at 6, right? And then they have a question mark. I'm guessing that's just for a space, I guess. They're putting spaces after each word. So so I'm guessing this is the thing that they're trying to find, right? So because they're able to search through it quickly, they're able to find the string with the try. I see. So CA bear, and then they're trying to find bear. So then you could just find that, and that's 6. So that's the thing. Word matching for prefix for standard try text to be searched. So yeah, so A is the text to be searched. B is the standard try for the words, which are known as stop words. With each external node augmented with the indications of their word positions. There's a potential space inefficiency with the standard try that has been prompted the development of compressed try, which is known for historic reasons by Patricia try. Namely, there are potentially a lot of nodes in the standard try that have only one child, and the existence of such tries is a waste. We discuss the standard compressed try next. So we're going to talk about compressed tries. So compressed try is similar to a standard try, but ensures that each internal node in the try has at least 2 children. It enforces this rule by compressing chains of single nodes into individual edges. So let T be the standard try. We say that internal node is redundant if V has one child and is not the root. For example, the try of a figure down here, if it has 8 redundant nodes, let us say that k is greater than or equal to 2. So these are all the nodes, right? It's redundant if V of I is redundant for I equal to 1. V of O and V of K are not redundant. So if V of I is redundant for, so if it has the same character, right, then, and the first and the last character are not redundant, then they're saying it's redundant. If any of the characters are the same in this sequence. So we could transform T into compressed try by replacing each redundant chain into a single edge and relabeling V of K with the concatenation of the label of the nodes. So here, okay, so before it was BEAR, right? Because of BEAR, because of AR is kind of redundant, right? Because I'm guessing it was repeated, was it? Well, okay, let me see. So it's redundant if V has one child and is not the root. Okay, so an internal is redundant, for example, if you have the 8 rows. So it's redundant if VI is redundant for V of I. So if it has one child and it's not the root. Okay, so that's what redundant is. So because of A had one child and it wasn't the root, that was kind of redundant. So they put that back up. So was L. It's kind of redundant, so they put that back up. So is this. Did they put I and L back up? Let's see. Okay, so yeah, so L was back up. They put L back up. BID, did they put that back up? Okay, so BELL. What's it? BELL. BELL. Okay, so that was also redundant, so they put that back up also. So yeah, that's what that was for. So that compressed the try. Thus, nodes in a compressed try are labeled with strings, which are substrings of the strings in a collection rather than individual characters. The advantage of the standard is that the number of nodes of the compressed try is proportional to the number of strings and not to their total length. So a compressed try storing a collection S of S strings from an alphabet of size D has the following properties. Every internal node of T has at least 2 children and at most D children. T has S external nodes, and the number of nodes in T is O of S. Attentive reader may wonder whether the compression of paths provide any significant advantage. It is offset by corresponding expansion of the node labels. Indeed, a compressed try is truly advantageous only when it is used as an auxiliary index structure over a collection of strings already stored in a primary structure, and is not required to actually store all the strings of the collection. So if the collection of strings are S1, S0, S0, S1 up to S minus 1, instead of storing the label X of a node explicitly, we represent it implicitly by a triplet of integers I, J, K, such that X equals S of I up to J up to K. That is, X is the substring of S of I, consisting of the characters from the Jth to the Kth included. Okay. So that's that. That's just talking about storing. It's a better way to store, right? It's indeed okay. The addition of compressing scheme allows us to reduce the total space. Okay. You only want to store the different strings and active chord and others reduce spaces. Okay. Okay. So let's talk about suffix trees. So one of the primary applications for tries is the case when the strings in the collection S are all suffixes of a string X. Such a trie, okay, did I say tree? I meant try. Such a trie is called a suffix trie, also the suffix tree or position tree of string X. For example, here it shows a suffix trie for 8 suffixes of the string minimize. For a suffix trie, the compact representation represented in the previous section can be further simplified. Namely, the label of each vertex is a pair, indicating the string. To simplify the rule that no suffix of X is a prefix of another suffix, we can add a special character with the $sign that is not the original alphabet at the end of the X. Thus, to every suffix, that is, if the string X has length n, we build a trie for this set of n strings. So, using a suffix allows us to save space by using several space compression techniques, including the one used to compress a trie. The advantage of the compact representation of the tries now becomes apparent for suffix tries, since the total length of the suffix trie is n to n plus 1 over 2. Okay, so that stores n squared, and even so, the suffix trie represents the strings, explicitly in the O of n space. Okay, so construction. We can construct a suffix trie for a string of length n with an incremental algorithm like the one given in the section. This construction takes O of dn square time because the total length of the suffixes is quadratic in n. However, the compact suffix trie for a string of length n can be constructed in O of m time with a specialized algorithm different from the one for general tries. This linear time construction algorithm is fairly complex, however, is not reported here. Still, we can take advantage of the existence of this fast construction algorithm when we want to use a suffix trie to solve other problems. So now we have this. And we could, basically they're putting, they're compressing it, right? They compact the representation for each pair, denoting here. So that's the suffix trie, okay? 771120. I don't know where the pair. Okay, so the compact representation represents a pair I and J. So the pair 4 to 7 is Mise, right? 4 to 7. The compression of Nimise is 2 to 7. See 2 to 7 and Nimise. Z is 6 to 7. So yeah. That's what they're doing. They're basically having a pair that denotes where it is. That makes it faster. Using a suffix trie. A suffix trie for a string can be efficiently perform pattern matching on a query of text X. Namely, we can determine whether pattern P is a substring of X by tracing a path associated with P to X in T. P is a substring if and only if the path can be traced. The search down assumes that the nodes in T store some additional information with respect to the compact representation of suffix trie. If node V has a label I and J, and Y is a string of length Y, associated with the path from this root to V, then x of j minus y plus 1 up to j is equal to y. This property ensures that we can easily compute the start index of the pattern in the text when a pattern match occurs. Alright, we're going to talk about search engines. Okay, so pages are gathered by a program called web crawler. Web search allows you to retrieve relevant information in this database, thereby identifying relevant pages given the keywords. We talk about inverted files. Core information stored by a search engine is a dictionary called an inverted text or inverted file that stores key value pairs where W is a word and L is a collection of pages containing a word. The keys worded in the dictionary are index terms and should be a set of vocabulary entries and proper nouns as large as possible. So elements in dictionary are called occurrence lists and may cover many web pages as possible. So you could efficiently implement an inverted index with a data structure consisting of an array of the occurrence of the items and the compressed trie for the set of index of the terms where each external node stores the index of the occurrence list of the associated term. Reason for storing the occurrence list outside the trie is to keep the size of the trie data structure sufficiently small to fit in internal memory. Instead, because of their large total size, occurrence lists have to be stored on a disk. With our data structure, a query for a single keyword is similar to a word matching query. Namely, we can find the keyword in the trie and return associated with us. So when multiple keywords are given, the desired output contains all of the given keywords and we trace an occurrence list of all of them. To facilitate intersection occurrences, each occurrence list should be implemented with a sequence sorted by address and with dictionary. In addition to the basic task of returning a list of pages containing given keywords, search engines provide an important additional service by ranking the pages returned by their relevance. Devising fast and accurate ranking algorithms for search engines is a major challenge for computer science researchers and commerce companies. And that's it. Please rate, comment, subscribe. I'll check you guys later. We're almost done with this. We just have 2 more days, right, man? Two more chapters. I might finish them today. I don't know. If we rate, comment, subscribe, I'll check you guys.